Hey there, in this lecture I'm going to describe what's called 1 Newton of force, and I'm going to describe it in terms of the pi space theory. Um, uh, the interesting thing about a Newton is it's a combination of two attributes of a pi shell. Newton described force as mass times acceleration. So what's very interesting about acceleration and gravity is that the when an object falls under gravity, um, the the weight or the mass of the object is independent of its velocity when it falls. So, for example, if you drop a feather from a height and you drop a brick from the same height at the same time, they will both fall at the same rate. Most people intuitively think that the brick should fall faster because it has more mass. Because if you hold a brick under gravity, and you hold a feather under gravity, the feather feels lighter. Therefore, one assumes that the feather should fall more slowly. Um, so, so the reason that that is not the case is that the acceleration aspect of force is independent of the mass aspect of force. So most of the pi space theory, if one studies it, one will notice that there isn't that much talking about mass very much through the whole theory. It's all talking about pi shells losing area due to movement, or an area loss due to acceleration. And the reason why we don't include mass is because the mass is inside the pi shell, and in the pi space theory, the mass component um, is responsible for the force of the movement, but it's not responsible for the actual movement itself in under gravity. So let's take an example of. But the important thing to know is if you're lifting something, if you want to do a calculation to physically produce lift, you can't just take into account the acceleration component, because you need to know how much the whole object weighs under gravity. A good example would be a plane. It has a certain weight, and therefore it needs a certain amount of lift in order to lift the lift force. So let's take the example of what 1 Newton is. It's typically based upon Newton's apple, which fell on his head in the story, and it's roughly 1/10 of a kilo under a gravity system, a gravity field of 9.8 meters per second squared. Uh, for the purposes of the discussion, let's just round up gravity to 10 meters per second squared. So let's just say it's 1/10 of a kilo uh, under 1/10 of a kilo of mass held in one's hand under a gravity field which is 10 meters per second squared. We're just rounding it up for the purposes of simplicity to give the idea of what 1 Newton is. Therefore, there's two aspects to the Newton. There's the 1 kilo unit, and then there's the acceleration, which is meters per second squared, which is the way an acceleration is described. When we multiply 1/10 of a kilo by 10 meters per second square, what we get is that the Newton is 1 kilo of mass per meter second squared. Um, Now that may be very intuitive to most people, but let's just try and explain in pi space how to visualize this, right? So so if one imagines a pi shell roughly the size of an apple, containing the mass of an apple, the amount of area loss. Now, this is the pi space side to it. If we want to understand what the force is mass times acceleration. So let's try and understand acceleration in terms of pi space. So the amount of area loss that the pi shell experiences as it moves in the direction of the center of gravity is always g over c squared per meter, right? So that is to say, if you move under gravity per meter, you will lose that the pi shell will lose g divided by c squared per meter of area. So the thing about gravity and acceleration is all that it maps to in a pi shell is its area and the loss of it. So you have a distance you travel under a gravity field as you move towards the center of the gravity field. You lose an area, and if you travel 1 meter, your pi shell will lose g divided by c squared area, right? And area equals energy. So what we get then from that calculation is 1 divided by g, which is 1/10 of g, which is 10, 1 over 10, times 10, which is the gravity field, 1 over 10 times g, which is 10 divided by c squared, and that works out at 1 divided by c squared. Now this crosses over a little bit into the Einstein work, where he showed that that gravity, the units of gravity were g divided by c squared. There, in some documents you'll see g divided by, I think it's g divided by 3 c squared, but the fully qualified version for pi space is 1 divided by c squared, and it's 1 divided by c squared of the pi shell. That's the amount of area loss that the pi shell loses, or the atom loses, over 1 meter. Now, so let's just try and draw this. So you can have a apple, and you can have an apple with 1/10 of a kilo in a gravity field which is 10 times which is 10 times the unit gravity field, 1 over c squared. So it's 1/10 times 10 times the area loss, which gives you 1 over c squared. Or in this case, it's 10 times 10 over c squared times 1 over 10. So the 10s cancel. So in practical terms, what that means is that when you have a gravity field in pi space, it's seen as an area that atoms move towards on either side of the gravity field, towards the center of gravity. And for each meter that the object falls, it loses it loses 1 over c squared per meter in a 1 Newton a 1g gravity field. But we all live in 9.8, so we rounded up to 10, so we lose 9.8 over c squared per meter in the Earth gravity fields. But in Newtonian terms, it's the Newtonian unit, it's 1 over c squared times an atom containing 1 kilo of mass. So it's not just about the area loss. That's the acceleration component. F equals ma. This is the a part, and this is the m part. 1 kilo. So 1 kilo is pushed into this pi shell. This can be millions of atoms, which make up 1 kilo. So it's 1 kilo moving in this direction, for example, or being pushed and compressed, and losing 1 over c squared per meter of movement, and it will continuously lose that per meter, and that's what an acceleration is, and that's how to describe a 1 Newton of force. So this is pushing down. So if you had your hand under here, you would feel 1 Newton of force. If you had your hand here, the line represents the area loss, and then it also represents the vector component, and that's 1 Newton. Just to recap, it's 1 over c squared kilo of force per meter. And this is important because we experience gravity also in terms of the mass that is inside the atoms or pi shells that contain the mass. So the more that an atom loses, in terms of its area as it moves in a particular direction, the greater the force that we feel. So it's that area loss times the mass that's inside the atom. That's 1 Newton described in PySpace. Thanks for listening.